So thank you so much, Alessia, for the warm welcome. And one of the reasons I'm always happy to be here at DLD is you bear it in your name, Digital Life Design. This is a comprehensive platform for talking about various issues, of course, innovation, but also politics, technology and politics. Thanks to the panelists from last one, I'm going to hunt everybody down from these excellent panelists. And this is a perfect background to talk about an initiative we took maybe 6 or 8 months ago when some Western European investment promotion agencies from cities and regions met in Vienna last summer. We had a serial entrepreneur with us, an American, who was very successful in the Silicon Valley and was now based in Taipei. And we were wondering if the Europeans can compete with China and the US in the technological sphere. And this guy was looking at us and saying, okay, you're a real chicken because you're not having the comprehensive approach. You're not looking at the whole value proposition of European cities and regions. It's not only about technology, it's also about quality of life, it's about the cultural background and healthy environment and so on. And we decided, okay, we're competitors in certain ways, but we also have to collaborate more closely. And what we also did, and part of today's panel is a part of this collaboration, we signed agreements with our dear friends from London and partner to collaborate more closely between London and Bavaria. And we might not have a common language in Europe within these regions, besides maybe the universal language of broken English. While we do have joint values, human rights. We have a reliable judicial system, at least mostly, and so many other advantages. And we also have entrepreneurial spirit and innovation. And this is why London and Partners and Invest in Bavaria organized today's panel jointly. Thanks for your efforts and brought in colleagues, renowned panelists and participants from quantum computing. So we are going to talk about innovation within this mindset of comprehensive collaboration on a European basis. And before anybody realizes that I have no clue about quantum computing, I want to hand over the stage and the mic to our renowned panelists. And Laura, my dear colleague from London and Partners, who's going to moderate this panel. Please welcome Laura Citron, CEO of London and Partners, on the stage, as well as Ian Walmsley, Provost and Chair for Experimental Physics at Imperial College in London, Ignacio Cirac, Professor at the Technical University here in Munich, but also head of the Director of Theory Division at Max Planck Institute of Quantum Optics, Torsten Siebert, Central Coordinator for the Quantum Technologies Programs at the Fraunhofer Society, and Sebastian Luber, Director Technology and Innovation, and responsible for scouting of quantum technologies. Thank you very much, and I look forward to the panel.
Well, thank you very much, Wolfgang, for your introduction and for your partnership. And what an honor to be here today with 4 of the leading brains in quantum computing in Europe. I'm sure we're going to have a great conversation. And before we start, it would help us to know who we're talking to. So I'm going to ask you a question. There are 2 options. Sorry, that's very binary of me in a quantum talk. If you have a professional interest in quantum, or you feel that you know the field pretty well, raise your hands. Okay. And if you feel like you're a quantum virgin and you're here to find out what the big fuss is, put your hands up. Great. That gives us a good idea of who we're talking to, which always helps. So before we get stuck in, I'd like to ask Ian to just tell us, what is quantum? What's the big deal?
Okay, Laura. Yes. first of all, it's important to recognize that quantum computing is fundamentally different than all kinds of computing we have used to date. It's not simply supercomputing on steroids. To quote Bill Phillips, who's a Nobel Prize winner from 1997, he says that quantum computing is as different from conventional computing as conventional computing is from the abacus. So where does it derive its power? If we think about digital encoding, we usually think about information being encoded in bits, so binary digits where each logical state, 0 or 1, is mutually exclusive. It can be either 0 or 1, and we build a physical system that has two possible physical states that can be either or. The difference in quantum is that it allows you to be both and. It allows you to have a superposition of these two logical states based on a superposition of the two physical states of the underlying system. That small change, apparently, leads to radical changes in the sorts of problems that you can solve. So it gives you a power to process and a compact way to store information that allows you to implement algorithms that you can't implement on a current computer. To give you a sense of what that might mean, if you take a register of, say, 128 bits, you have a program that runs in a certain time on that register. You might have a problem where if you double the size of that, a conventional computer needs to grow by size about a factor of 4. Or if you triple the size, it needs to grow by a factor of 10. A quantum computer could take that same algorithm, it's not every algorithm, but special quantum algorithms, and simply run a factor of 3 bigger register on a computer that's only a factor of 3 bigger. So it's a step change in what we can do, not just an extrapolation of what we know now.
It's fascinating, and as I've been reading about it, the possibilities seem almost endless. And one of the analogies that resonated with me was that it's like the difference between a candle and a light bulb. 1,000 candles will never equal a light bulb. They are fundamentally different things. So why does it matter? I'm going to ask Sebastian, Torsten, Ignacio to just give us in 30 seconds the application of quantum that most excites you. Sebastian.
Yeah, so as mentioned, quantum computing is fundamentally different. So it's very strong in solving problems, solving challenges where currently classical computers fail. So for me, the most fascinating topic is with regards to optimization. For example, in layout optimization or finding the shortest path. This is really fascinating where quantum computing could make a difference, I think.
Oh, you've lost your mic. Torsten.
Right, yeah. Optimization is a really interesting word. And I think what I like so much about it is it's kind of reflected maybe in the physics of the two different systems, digital and quantum. The digital process, the transistors, the switching is always decoupled from one another. Yeah, information cannot be taken as a whole. And the quantum system can really consider the dynamics and the evolution of a very complex system and considering its components simultaneously. And that's just so universally transposable onto finance, onto material science, onto transport network optimization. It's fascinating how things that we just think are too complicated now can become accessible.
Fantastic. Ignacio.
Well, this is a technology that is emerging, and I think that most of the applications are still to be discovered. So right now, what we have been able is to cross a border where there's something completely new and unexplored. We know a couple of applications. We know certain problems where a quantum computer would be fantastic, but I think that there are many that are still to be discovered. If I had to select one from the ones that we know so far, I would select just chemical reactions and the structure of chemical, let's say, drugs, for example. So that's something that supercomputers, so you want to design a new drug, I mean, they cannot do that because this requires a kind of exponential power, and that's something that it's not available in these supercomputers. However, a quantum computer using the rules of quantum physics, using a different laws, can afford to solve these problems, and I think that this would have many, many applications.
Thank you. So these applications have potentially life-changing and system-changing implications. And for those of us who were in the panel before, I think we heard a really powerful illustration of what happens when a major technological leap ends up very concentrated in American monopolies and the Chinese state. And so the question that we really wanted to explore in this conversation is, what's the future for European quantum? Where are we now? What's our ambition? And how can we realize that so that in 20, 30 years' time, we're not having the same conversations about quantum, Europe, and values that we are perhaps having about the internet today? So starting with Ignacio, you are at the center of many European research networks and the science behind quantum. Can you just give us your state of play of today? How is Europe doing?
Okay, so quantum computing at the moment is at the stage where science the basic principles have been laid down, and now it's time to make the next step and to take it to the industry. I think that Europe is very well off in what is science, so it has contributed very actively to the discoveries and development of the field through many networks in Europe, many supporting measures from the different European governments. So it's a very good starting position for that. Now the next step is going to the industry. That's where, I mean, we have to see what is the environment around it, what are the funding possibilities. So Europe has a different system than the US and China, so how to compatibilize the situation, and I think that that's the good, I mean, the question that we are going to discuss probably here, but it's a very, very important question.
So we're in a good place now. Ian, what do you think it's going to take for Europe to maintain a leading position as we move more into the application and the computing of quantum?
Well, I think if Europe has an ambition to be a leading player in this domain, then we need to be coherent about stating that ambition, and then working together to realize it. So one way to do that might be to say that Europe wishes to build a quantum computer, and then to coordinate activities to draw upon the excellent science that Ignacio has referred to, and the SMEs that Sebastian has noted, to bring together that in a coherent way. Europe has done that in many other domains, the fusion domain, fundamental particle physics, and other sorts of organizations that can draw together these threads. Couple that with a significant investment, whether that is private capital or state money or some combination of both, I think that concentration is needed.
Give us a number.
I dare not, but you can look at perhaps at what Google has invested. They assembled a team over 3 years of about 60 people. You can imagine what kind of cost that is, and that's got us to a point where the first demonstration of a machine that can outperform on a toy task a classical supercomputer. I think you need to now think about multiplying that by orders of magnitude, and you get to where you need to be.
So we need an ambition, and we need to invest. But Torsten, your focus is all about the application of research. Is it all about money? If we 10x the money, would that solve it?
I mean, money always plays a role, and it's a high-end technology. It demands a lot physically as well as from the community that's trying to develop it. But I think commitment is clearly an issue. We talked about China and the US, and there we have either strong economic commitment or strong political commitment. And I think in Europe we need to be clear what motivates us toward this technology. We need to find our motivation, and when we have that motivation, follow it. Also beyond money, I think this is the most important component, are how the ecosystem works together. on this. And here with Fraunhofer, we kind of try to fill in the gap, so to say. Yeah, we have, that we talked about, the excellent European science that has pushed in fundamental science this topic so hard and has performed so well. And on the other side, we have very prominent industry that's willing and interested in taking up this technology, and now we just need to find how to fill the gap so that this technology can flow in Europe. Yeah, because I think everybody's excited, everybody's interested, and we want to create, especially at Fraunhofer, we see it in our mission, to create the environments where the critical components of basic knowledge and area of application come together.
So to keep this flowing, turning to you, Sebastian, you are the quantum innovation scout for a major semiconductor business. First of all, that sounds like a great job.
Definitely, yes.
Tell us what are you looking for, and how ready are you to apply what you find?
It's fascinating because if you think about quantum computing in a broader context of quantum technologies, it is already having an impact. So you also count, for example, sensors to these quantum technologies, where you already see first evolution of having more precise, highly sensitive sensors. So you could think about new applications. But if you think about quantum computing itself, as already mentioned, the potential is extremely high. And one of the most mentioned applications is this impact towards encryption. And we are a major supplier of encryption solutions, of security solutions. So we already prepare right now for a potential future universal quantum computer to be resistant to their possibilities, which is possible. So you can already develop now encryption possibilities for that purpose. But also as a supplier of components, every quantum computer needs a lot of standard electronics. It needs a classical computer to run. And there we are also very strong in certain components. So we also think about going into this market, about providing components for quantum computers. And last but not least, it's also about the application. So we have a lot of problems to solve where we are heavily struggling with the possibilities of high-performance computing, of standard computers. So we are already looking into this. How could we make use of already existing noisy quantum computers to get there an advantage?
So you're already looking at the commercial opportunities around encryption and supply chain. But what you're not doing is investing in building a quantum computer. And as Ian said, part of the issue is, do we have an ambition in Europe to do that? You are working on a partnership between Fraunhofer and IBM. Can you tell us a bit about that and why you've chosen to take the route of partnering with IBM?
Right, gladly. I mean, in the last question, I tried to emphasize the importance of community and network and opportunity. And our motivation for going together with IBM is that we have a high threshold technology. And I think for a long time now, particularly on the application side, people ask themselves, what can we really do with the technologies? And we see at Fraunhofer that we have the necessity, in order to motivate the efforts in Europe, to evaluate the current state of affairs. What can we really do with the state that we have now? It's a very exciting state. We have an intermediate phase, as you already said, and then a noisy intermediate stage technology where the game is fully open. We're not even agreeing upon right now, I think, of what's even the optical physical way of realizing a quantum computer. We have all directions to take. And if we now provide a platform with a low threshold where really also the players that are usually not on board, like the small middle scale industries, the startups, the universities, who are seeking to look at this technology, they want to use it, they want to try it out. If we give that platform that we're going to supply with IBM, which we're very excited about, then we see the possibility of getting a first iteration of what we want to do with this kind of technology in Europe.
So the partnership sounds really powerful, but Ignacio, to ask perhaps the provocative question, by partnering with IBM, Is Fraunhofer selling out the European quantum dream here?
Well, I don't think so. I mean, it's not because you're here, but I think that at the moment, I mean, what happened is that the next step, building a quantum computer, I mean, has started in the US and some extent in China, but not so much in Europe. And so you want to catch up, we have two options, either to start now and maybe in 3 years we're at the stage where the Americans are, or we can just buy what they have at the moment and try to get faster where they are. And I think that that's one very clever strategy that Fraunhofer is taking. Yep.
Do you agree?
I think there are many routes to this end, and we ought to pursue as many of them as we can.
Very diplomatic.
Maybe I can add on to that one more time. Yeah, since the provocativeness went in my direction, but I was supported by my colleagues, I'll just aftermath that I think a plurality is what we need. The IBM strategy is we're very happy that IBM is bringing the technology. We think it's an excellent platform to work on. At the same time, Fraunhofer is also pursuing with fundamental science, trying to do our best to give technology to fundamental science to realize the concepts of European quantum computer. And I think that's important. I think it's the interaction of all knowledge that we can build up in order to achieve truly our goal of having a European quantum computer.
So we need, for the moment anyway, a pluralistic approach, but one that's built on European collaboration. And I'm interested to hear from your point of view, Ian. You and Imperial sit at the heart of a whole range of European collaborations around quantum and many other things, including with the Technical University here in Munich. How do you see European collaboration evolving, and what could be done to improve the way that we're collaborating in Europe on quantum so that the whole is greater than the sum of the parts?
Well, I will take as my starting point Ignacio's comment. So the basic science and underpinnings of quantum information were largely laid in Europe. And that has enabled the building of networks which I think are very strong, and certainly at the component level have really pushed the envelope. So the highest performance quantum gates are currently, the records for those are currently held by European groups. So the stage that we now need to move on to is how do we get that together to really deliver a machine? And Torsten's noted an important part of that, which is how do you build a community which knows and understands how to use such a machine and what it can be used for. That, I think, gives a pull to now the next stage of the technology to develop. The previous panel noted some of the challenges, and you've alluded to them, Laura, as to what happens if that capability lies outside Europe. And so there's not only the market driver, but there's also the capability driver, which may have security implications. And I think that's also one where there's a great public interest, which is why some combination of probably public investment to help drive that and private investment to allow that pull is going to be key. But I think that has to gel around a clearly stated ambition and a locus for such a machine, whether that's in a major European corporation or whether it's in a national laboratory or whether it's a pan-European laboratory, I think is the stage, the decision we now have to make.
So the question is, what becomes that focal point in the way that perhaps CERN has done for that industry? Sebastian, from the private sector point of view, do you see any possibility of that locus for European quantum being in a company in the private sector in Europe? And if not, why not?
I think there, of course, you have to focus on the competence which you have in your company, on the strength which you have in your company. And unfortunately, we don't have this computer builder as we used to have, who has the competence to fully design a system. So this holds true as well for quantum computing. Nevertheless, I think, for example, by startups, this gap could be closed, and this is exactly what we have to work on to create their low entry barriers for startups regarding IP, regarding state-of-the-art production capabilities, to enable this system competence to be built. Because I fully agree that we are very good, extremely good in basic science, but in this commercialization of the science, so in creating a company who is leading the field, there we have a trouble. And if we would have that, then we wouldn't have to discuss about sovereignty, about technology. If you have it in Europe, then we wouldn't have to care so much about US or China.
So it could be done within a business in Europe, but that business probably doesn't exist yet. Or if it does, it's still very small. It's not an existing European business that's going to take the lead on quantum in the way that IBM, Microsoft, Google, Amazon, Alibaba have made really significant investments in commercialization.
I think there are already significant startup activities in Europe as well. You have in Innsbruck, you have in Finland, some startups working on ion trap quantum computing, on superconducting quantum computing, and also all venture capital flowing into it. But of course, compared to the situation in the US, the amount of venture capital is far low. And as we heard earlier this morning, also the venture capital into really developing something new, not applying the existing stuff, is also quite low. So I think there we definitely have to improve.
So maybe I can say something about that. So building a quantum computer, the one that will have these applications on optimization, on security, and so on, it's a huge challenge. It's not something that will happen in 2 years, nor maybe 10, maybe it takes 20 years. So it's not a question now that say, okay, let's put a lot of money and let's do it in 2 years. It's a little bit, I mean, people compare it to what happened when for the first time, I mean, some people were able to fly for, let's say, 10 seconds or something like that. So that was happening in quantum computation. So the first demonstration that something can fly has happened. And from there to go to a commercial plane, it's a huge investment, many things have to happen. And so people are positioning at the moment, and the different countries, the different companies are positioning, but knowing that that's a very long enterprise. But at the same time, it turns out that since this is a new thing that is happening, there are things that are popping up that maybe have commercial interest before this quantum computer is built. And I think that that's where there's the opportunity, where these startups are coming up, where things are happening, where there's a lot of vibration. And I guess that it's not only thinking about how to build this quantum computer in 20 years or 30 years, but rather let's take opportunity of the things that are coming up and let's pay attention and be prepared in a good position to follow that.
But perhaps may I add, we also have to question ourselves, by having access to the hardware, do you get a speed advantage over others which just rely on existing hardware? So if you're at the forefront of the hardware development, could be, as the quantum computer is so completely different from another computer, that you see things which might be valuable to sell, to commercialize, which you don't see if you are at the forefront of the hardware development.
That's right, but this is what I'm saying, that we have to be prepared for the developments. That's not the quantum computer, there may be something else that pops up, and I think that can have economical interest.
Fantastic. Well, hopefully we now have a better sense of what some of the key issues are. I'm going to throw it open. We have a few minutes for questions, if anybody would like to ask this illustrious group. Yes, please. Sorry, I don't think we can hear you, but you're Pam, and you want to ask a question about security. Tell me who you are, and I'll repeat it.
I'm Pam Dillon.
She's Pam Dillon.
I'd like to understand the implications to war.
And she's asking a question about the implications for war, which is an interesting one, because you touched on the security and how that might be a major constraint in the development of quantum. Who wants to take that?
Well, let me, I won't try the macro question, but I will perhaps be able to say a few words, and perhaps Ignacio too, on some of the things. So one of the very early algorithms, perhaps the one which really tipped the interest in quantum computing, is something called Shor's algorithm. And that was a demonstration, in theory, that there existed an algorithm which could efficiently crack public key crypto systems. Now, Sebastian has noted that there are other ways of encoding which may or may not be immune to such algorithms, but that's one way. So in other words, all the information that you thought was secure is no longer secure, and that extends backwards to all the information that you encoded using those encryption algorithms. That's one thing. But as Arthur Eckert likes to say, the quantum giveth and the quantum taketh away. So there is a technology that Sebastian referred to called quantum key distribution, which allows you to distribute information between two parties in a way that is unbreakable. So there are different aspects to this which to deal with the security of information, which could have an impact on conflicts for sure, but is probably broader than that too.
What do you think, Pam?
I don't think we know yet. I think it has to be part of the conversation.
Yeah, to those who couldn't hear, she doesn't know yet, but thinks it should be part of the conversation. And I think one of the things we've skirted around in the previous, in this conversation that was very clear in the previous one, is that no technology is neutral, and that we have to put ethics at the beginning of the conversation as we develop quantum. And I'm sure that as this conversation develops, part of the driver for having European quantum industry is that we can build a quantum industry around our own values. Do you want to come in?
Yeah, I would take a perspective on that too. Anne comments so nicely quantum information distribution as well, yeah, using quantum key distribution as a secure communication. So one can actually put the computer in a larger context of quantum information in general. Its communication as well as its processing in a quantum computer. And Fraunhofer, for instance, is very active in the communication aspects. We're right now working together with the federal ministries in Germany to make a quantum secure communication in the network of the ministries, so for the federal government. Yeah, that's taking place right now. And what we kind of see at Fraunhofer is one can take, of course, the threat that the computer poses by its capability to factorize numbers, or one can also say quantum information as a general could be a new standard where maybe we don't have to repeat the mistakes we've made in building up our digital systems that we have to date, our classical ones. Yeah, if we look at how digital systems developed, we never thought about security when the transistor came. Yeah, and this network just blew up on us. Yeah, and right now at Fraunhofer we see in the security institutes that do IT security that it's just this endless resources of protection, resources of the attacker, resources of the protection, and it's a never-ending cycle. Yeah, and with quantum, that whole game could be broken. Yeah, because it's a fully different standard. The way it's communicated is it's a physical type of security. It's not an IT mathematical structure or strategy that's guaranteeing the security. It's the physics of quantum and entanglement that's guaranteeing the security of information transport. And I think similarly, when we start thinking about quantum computers and integrating those maybe into our infrastructures, we can bring in the security before and not in aftermath. And that's a big chance. Mm-hmm. Yeah.
Thank you. I think we've got time for one more question. Gentleman in front there.
My name is Marco Walmsley. I'm a technology journalist and business journalist from Switzerland. I would be interesting to see, when we look back what happened with the introduction of the internet, it changed profoundly the way societies live, the way societies work, people date, people do shopping, etc., etc. Are there any ideas yet how quantum computing will shape or change societies?
Well, I guess that if you had asked the same question, I mean, as the very beginning of internet, they could not have imagined what we have now. And that's a little bit the situation that we have now. So if I tell you, all of a sudden, you have the capability of a computer that can do everything billions of times faster than a supercomputer. So how this will change the society? Well, I personally don't know, but I'm sure that it will.
Yeah. I would agree, it's very hard to predict how it will do it. At the moment, I would say people are focusing on known tasks that will allow us to do better. Ignacio mentioned simulation of molecules. Well, if you can do that better and understand target structures for drugs, for example, maybe you have better healthcare through it. Maybe you have better data security for more personalized medicine. So those are taking what we know now and taking them into that new domain. But I'd agree with Ignacio, there's probably any number of things that we just can't quite see at the moment that this is going to radically impact. Yeah.
So just to wrap up, I think it's clear that Europe is in a great place on quantum science, and we have a real opportunity to lead in the development of quantum computing. But to do that, we need to collaborate. Collaboration alone won't be enough, though. We need ambition, we need coordination, we need money, we need focus. And ultimately, it comes to a question of priorities. Is this industry one which we are going to prioritize for funding and for our attention? I'd like to close by thanking again Wolfgang and our partners and colleagues at Invest in Bavaria for bringing us together. I'm really proud of the role that the UK and London can play in the development of European quantum computing, and delighted that Ian's here with me. And despite the UK's relationship with the EU being one that is perhaps akin to superposition at the moment, you can tell who the quantum Brexit geeks are in this room by who laughed at that joke. London is and always will be a European city. And for us, thank you, Steffi. And that's why for us, these kinds of conversations and these kinds of partnerships are so important. Hold on, another quantum Brexit joke coming. I think London is entangled with the rest of Europe, and it always will be, and that is for the better. Thank you very much to my panelists today. Genuine experts, fascinating conversation. Thank you to all of you.